morning, everyone. The paper we will discuss today is Overview of the SPARC Physics, basis towards the exploration of burning plasma regimes in high-field compact tokamaks. If you have any questions, I'd be happy to hear your comments. Section 6. Stability and Disruptions. The use of the high magnetic fields opens a wide window of high-performance operation with comfortable margins to disruption limits. In particular, the low normalized beta Bn equal 1.05, low normalized density Fz equal 0.37, and moderate safety factor Q equal 3.4 of the PRD scenario reduce instability devices, resulting in an expected lower frequency of disruptions. Nonetheless, the disruption loading in SPARC is comparable to ITER, and therefore all tokamak systems are being designed with a level of passive resilience suitable to withstand the predicted loads from a realistic number of both mitigated and unmitigated disruptions. The compact size of SPARC results in short thermal quench and current quench durations, with empirical estimated lower bounds of bigger than 50 microseconds and bigger than 3.2 milliseconds, respectively, although empirical scalings suggest a possible favorable effect of the toroidal field, as they often have allocator C mod with a field of up to 8 Tesla as an outlier. The engineering design of SPARC will not take credit for this and instead will utilize empirical probability disruptions for the quench durations. Similarly, SPARC structures are being designed to withstand the highest predicted forces and torque caused by eddy currents. SPARC plasma-facing component design is working to trade off reducing eddy current torque in plasma-facing material by reducing unit size and increasing unique part count by making tiles overly small. Large first wall components such as limiter and diverter support structures, ICRF, antennas, port, and vacuum vessel are being engineered to withstand use those loads peak Harrow current of substantial fractions of the plasma current up to 50% with peaking factors of 1.4 in rare events are expected following vertical displacement events. High attenuated axisymmetric vertical forces of up to 35 meganewton could be possible. The vacuum vessel is also being engineered, accounting for these loads with multi-physics analysis to examine in detail the electromechanical laws, in particular contact points and Hello current phase passes. Runaway electrons pose an important challenge for tokamak operations and arc survival, and SPARC was multiple advantages as a facility to study solutions to this problem at reactor scale, even though modeling work suggests a favorable effect of the high elongation in SPARC. They can cause scenarios damage to PFC materials. However, SPARC does not have actively cooled PFCs and can endure damage from RES without risking loss of coolant accident. The design of the passive runaway electron mitigation coil REMC is underway, as modeling results are very encouraging. The REMC is able to mitigate or even suppress the runaway C by applying three-dimensional non-asymmetric error fields that deconfine RES by breaking up flux phase into widespread stochasticity. Time-dependent magnetic fields from COMSOL simulations of various REMC configurations and provided for nonlinear MHD modeling with MIM-ROD. Recent simulations show that a coil with dominant N equal 1 toroidal mode number perturbations, as the one shown in figure 4, drives a stochastic loss rate that exceeds the avalanche growth rate, preventing exponentiation of very small speed populations. Figure 4b and c shows a long-lasting stochastic field disruptions. After the summer quench, work is ongoing to assess the full evolution of the RE beam and the integration of the REMC in the tokamak, including its compatibility with plasma initiation. SPARC will begin operations using massive gas injection for disruption mitigation, but is being designed to enable testing of other mitigation techniques as future upgrades. Regarding of other mitigation techniques as future upgrades, regardless of the approach to trigger the mitigation actors in a timely manner, work is underway to develop disruption prediction along algorithm that can provide warnings in real time prior to summer quench. The SPARC team is leveraging data-driven algorithms to robustly predict transitions to unstable operational spaces, following the success of similar techniques in current devices, achieving bigger than 90% of true positive rates in some machines. Transfer learning techniques to average existing data to extrapolate to SPARC are being evaluated. Thank you for listening to the end of today's show.